Do I have all the submissions for the homework assignment here? Anybody else have a paper? All right. At the front, I was giving back your old assignment. If you don't have that, you can pick it up after class. Here is the old in-class exercise. You can collect that later. What you do need for today is the notes, the in-class exercise, and the new homework assignment. So does everybody have, at the very least, a copy of the in-class exercise for today? All right. Great. Well, let's go over a few announcements. We have an exam on Tuesday, and hopefully that's not a surprise for anybody. We've been leading up to it all semester long. It's here in the classroom at 12 o'clock, so don't be late. You'll only be hurting yourself if you come late. There's two parts of the exam. I'm going to have two stacks of paper. One stack is the concept portion of the exam. I'll give that to you at the beginning. And when you finish it, you give it back to me, and then you can start on the problem solving. And the reason why I keep it separate is that you're allowed to make an equation sheet for the exam, and it can have actually equations, definitions, whatever you want, but you can only use the equation sheet on the second part of the exam. So on the first part, where I may be asking for short answer or explain something, you're not looking at the formula sheet for that one. All right. I think the air is clear now. We can probably close those windows. All right. Will you close that window back there? It was a bit stuffy at the beginning. Okay. So the other thing I wanted to mention is that there's a new homework assignment here: sedimentation, filtration, disinfection. Now, here's the schedule for where we're at in the semester so far. Today is class 15. So today's lecture is included on the midterm exam. Excuse me? Okay, so today's lecture is included on the exam, but you haven't turned in the homework assignment yet for, homework number 7. So the calculations that go along with sedimentation, filtration, and disinfection, that calculation stuff isn't on the exam because you haven't done the homework yet. But the concepts are. Because we're going to talk about today the filtration concepts. Disinfection concepts won't be on the exam. So basically, the rule of thumb is everything that we've done prior to the exam is included on the exam. But things in the future won't be on the exam. Not yet. Okay? Is that clear? Anybody want to ask questions about our midterm exam that we're having on Tuesday?
The three types of mix production, but the equations for each one.
Uh-huh. Yeah. I would encourage you to copy over all of the equations for kinetics and reactors. Yes. And so if it's a production reaction versus a consumption reaction, you either need to, in your mind, know that the K value will either be positive or negative, or you can write the equations separately as a production or consumption reaction. You can get the right answer either way if you keep track of that the K value is negative for a consumption reaction. Yeah, you need, if it's a formula, you should put it onto your equation sheet. The exception to that is I'll provide you with a periodic table if you need one. So you don't need to transcribe the periodic table by hand. You don't need to do that. The other thing that I'd give you is a chemical reaction. So, for example, the reaction of coagulation that uses alum, consumes alkalinity. I'll give you any chemical reaction that you'd need to refer to. Any other questions about the midterm? Yes. Yes. I'm wondering if I brought the solution to today's homework. I did. I brought it. I'm not willing to post them online, but I can. At the end of class, if we have time, I'd be happy to have you look at it. If you want to come up and look at it, or I could tell you the answers. But I'm not going to post the solution online like as a PDF. So, yeah, if we've got some extra time at the end of class, then we'll go over it together. If not, individually, I'd be happy. You can stop by my office and look at it. I'm going to be in my office all day grading another assignment, another exam. So you stop by and you can look at the key. or come by tomorrow and look at it, or just immediately after class. That's what I'd suggest. Let's talk about what happens in water treatment after sedimentation. So we're basically just going through all of the treatment systems to take water that is turbid and making it clear. Remember that the whole point of sedimentation was to remove those flocks. We were talking about circular particles that settle downward, and why is it that we want them to group together? Can anyone remind me why it's better to have groups of particles instead of just an individual particle? It's right, it settles faster. Why does it settle faster? Okay. Right. Remember from the formula, it's the diameter squared that says the settling velocity. The formula that we had in the last in-class exercise, it relates to the density of the particle minus the density of the water, diameter squared divided by 18 times the viscosity. So if we can get those particles to have a big diameter instead of a small diameter, then the settling velocity is much faster. If we double the diameter, the settling velocity is 4 times better. So we want to get those particles grouped together, but something's always going to slip through the cracks. Even in the finished water, there's going to be a little bit of turbidity remaining. And so we're going to talk about filtration now. And in filtration, it's a process of straining particles. This usually when people talk about filtration, they're thinking by the process of straining. Maybe some of you here have watched as the oil filter gets removed from a car, and the purpose of an oil filter is just to remove the little bits of carbon, and if there's bits of metal that somehow are coming off of the cylinder, it all gets trapped into the oil filter. But this kind of filtration is a little bit different from the kind of filtration that happens in water treatment. We're not necessarily just talking about straining, but to give you an idea of what it looks like on the inside of an oil filter, there are these fabric media pleats, and the particles get stuck because here the particles have a larger diameter than the media. The media has holes in it, and the liquid can go through the holes, but the particles can't. That's what we mean by straining, is it's a difference in size that causes the removal. And so here you can see oil that's been filtered and unfiltered oil that has a lot of suspended particles in it. So particle straining is one kind of filtration, but that's not what happens in a sand filter for water treatment. It turns out that the particles are too small. We can't remove them by straining because sand particles are very large. So how is it that you can use big sand filters to remove the tiny particles in water treatment? Sometimes we also talk about filtration when it's a chemical absorption. And earlier in the semester we talked about activated carbon and how organic chemicals will get onto the surface of activated carbon. And that's not the kind of filtration we're talking about either. What we're talking about is particle impaction and adhesion. And I've got a couple of animations that illustrate what I mean, but when we say filtration, it's only a filter in the sense that a small particle is being removed. It's not straining that happens, but it's actually particle impaction. So let me dim the lights a little bit further so that everyone can see. The diagram's a little bit small. On the left, all those little dots, that's meant to mean sand. So here is sand. What is the empty space between the sand particles? Do you remember the technical term for that? Voids. Right. So this is exaggerating the size of the voids. In reality, the voids are approximately the same size as the sand grains themselves, maybe a little bit smaller. So here we have a column of sand, and by a column, I mean that we're just considering a vertical orientation. The water is going down through the sand. We have the water pooled up above it, the water is going down, and the particles are in the water. So here's our particle. This is a little bit of extra turbidity that made it through flocculation. Just for whatever reason, maybe it never had an impaction, Maybe it got broke apart because we stirred it too quickly. It could have been sheared apart. But what we know about this particle is it's still destabilized. It still has all of the positive charge surrounding it from coagulation. Remember, we chose alum and iron because the particles were had a negative charge on the outside of them, and alum and iron both have a +3. So here is the path. The dashed line represents the path that the particle takes as it's traveling through the sand filter, and then it impacts the sand. And because of that collision, now it's stuck onto the surface of the sand. It actually is attracted to the sand, and so there's lots of different particles. Maybe some of the particles are removed early in the sand. Maybe just by coincidence, the path traveled by the sand, by this particle, as it gets almost to the bottom before it's removed. But there's a whole range of particles, and some of them may even get through. In the end, some of the particles might be removed. Is that the homework there? No? Okay. Something else. All right. So some of the particles are going to get through, but the majority of them are going to hopefully be removed so that we can make sure the water is pure. The review here is the water is flowing downward through a multimedia filter. And multimedia means it's not actually only sand that's inside of this filter. We'll have crushed gravel at the bottom, and at the top sometimes they'll add a layer of crushed coal, anthracite coal, just to try and make it so that the void sizes are smaller, so that there's a range of particle sizes. But these particles will stick to it, even though they're not strained. So our goal is we want to, when the water comes out of filtration, we want it to be less than 0.3 turbidity units. And turbidity units is just a way of measuring how clear the water is. And they do that measurement by shining a light through it. And if you have a beaker of water like this with lots of particles, and you shine rays of light through, then maybe only some of the rays of light will get through because some of them will be intercepted by particles. You know, maybe there was a particle here and that ray of light gets stuck. And this one gets stuck here, but some of the other ones get through. And so if you know the ratio between how bright it was initially and the intensity of the light when it comes out, you can calculate the turbidity from that. And so water that's very low on particles will have a higher clarity than the turbidity is going to be very low. So 0.3 turbidity units just means there's not very much particles floating around in the solution. Here's a picture of anthracite coal when it's crushed. Sometimes they'll use anthracite coal, sometimes it's activated carbon, and when you use activated carbon there's a double benefit. The benefit being that not only do you have a variety of void sizes, but also you can remove any dissolved organic chemicals, like if there's pesticides in the water that has to be removed, or you know, if there's any kind of fertilizers that were in the runoff that needs to be removed. So here's a cross-section of a typical sand filter. The water comes in and forms a puddle or a pool on top of the sand, and it's just hydrostatic pressure that forces it downward through the filter. These troughs are used to remove water during backwash, because sometimes the filter gets clogged. Like if we have, here's our cross-section that's representing sand. If you have lots of particles over the long term, you can imagine that all of these voids would begin to get filled up with the colloid particles. And when there's no more voids, then the water can't pass through any longer. Actually, as the void space gets lower and lower, then the pressure required to force water through the filter increases. They call that head loss. And you can measure basically how deep the water has to be in order to get a certain flow rate out. And you may remember Darcy's law, that is an expression of how easily water passes through a soil. And it's a similar concept here, that the deeper the water has to be to get the flow rate through is a reflection of void size that's remaining inside of the filter. So let's take a look at this animation, then we'll come back to the cross-sectional view and talk about the pieces a little bit more. All right, let me dim the lights so we can see the animation a bit better. This is a cross-sectional view of the filter. So in this animation, the water is coming in through this pipe, and it's actually okay for us to just use a normal pipe this time. We don't have to put any special baffles in like we did when we were talking about flocculation and settling. So the water is coming in, and now there's a certain depth of water, and it looks like this is a dual media filter. They have a layer of sand, and here is a layer of gravel underneath the sand, and there's a slotted pipe at the bottom of the gravel, and so the clean water passes through the slotted pipe, and then here is a tank that's storing the water that's been clarified. Halfway through the cycle, they're going to start seeing that all of the filter is clogged, and so they're going to have to stop the normal water from coming through, and they're going to backwash the filter. So let's watch that animation. Okay, the particles are coming in. They're getting stuck in the sand filter. The sand filter gets more and more loaded and dirty, and so they have to clean the sand filter by turning the water the other direction. So they're cleaning it, shaking loose all of that turbidity, and the wasting water goes, maybe there's a secondary process to clean the wasting water. Yes? That's right. Yeah, it's to remove remaining particles that were there even after coagulation and flocculation. So these particles are the ones that escape from settling. They're the ones who didn't hit the bottom. Remember that to be considered removed, it had to hit the floor of the clarifier. So those are the ones that didn't make it to the floor of the clarifier. In reality, what's going on when we have the water flowing the other direction is we put the water through at a very high velocity. And it makes the sand kind of like, they call it fluidize the bed. The sand starts to be suspended because we push the water through fast enough that it makes the sand raise up and it starts swirling around. And so the sand is floating and the sand is banging into other sand particles, and it's kind of scouring off the particles that are stuck to the surface of the sand. And so it's a kind of a delicate balancing act, because if you put too much water through, then the sand will overflow off of the outside of the filter. But you want to have enough velocity that you can actually fluidize the bed and clean it off. So let's go back to this diagram here. So these troughs that are here, that's to remove the dirty water during the process that's known as backwash. At the bottom, you can see at the very bottom of the filter, there's these blocks that have slots in them. That's just so that the water has somewhere to pass through, but you have to put together a structure that's strong enough to hold a layer of gravel and a layer of sand. So the water comes in. There will always be another pipe that allows you to fluidize the bed afterwards. But we can break these processes down into the filter phase and the backwash phase. And this is just talking a little bit more about the backwash phase and why we do it. The purpose of the backwash is to increase the void sizes again once it gets clogged with all of the particles. And so it's just the process of taking a pressurized water source. It doesn't have to be from an elevated tank. We could use pumps. But this is just illustrating that the water is at a higher pressure and so the velocity going up of the water during the scour phase is much faster than the usual flow rate that's going down. The loading rate that we'd usually apply to the sand filter is a much slower process. So we pump the water up through the media. The particles collide, meaning the sand that's covered with like a coating of colloid particles. It's kind of dirty sand. The dirty sand is floating around during backwash and bangs into other sand particles, and then those particles that were stuck in the sand filter get wasted into either, you can send it to wastewater treatment, or you can put it into a river, because really all it is in many cases is clay particles. But because of conservation efforts, it's becoming more common to try and concentrate the solids and then reuse the water a second time. So just putting the water at the beginning of the treatment step. Mm-hmm. So you're saying take the water from the backwash and put it in again? Yeah, they'll do that, except for you have to separate it somehow, because if you took all of the backwash, including the particles, then it would be like a loop, and the particles never get out somehow. And so there has to be some way to take the particles out, or else there's an accumulation. And so the backwash, sometimes they'll try and concentrate like through vacuuming out the water, or sometimes they'll put a sludge through a filter press and try and squeeze the particles so that the water can be recycled, but we can't send the whole stream to the very front. Otherwise the particles would accumulate. Okay, here's sort of the design process, or the sizing process. There's something known as the loading rate, and this is very similar to what we were doing with the clarifier. Yeah, when we had a surface area of the clarifier, the loading rate there was just the process flow rate Q divided by the bottom surface area of the clarifier. It's the same thing here with the sand filter. We can classify what kind of a sand filter we're doing. In the past, they would put very little water through sand filters, and they relied on good performance being by straining. This is kind of an old method that isn't used very often any longer. There are a few cities that still do slow sand filters, but now we use rapid sand filter because through coagulation we don't have to rely on straining. Straining is very difficult to achieve when the particles themselves are so tiny. So if we rely on destabilized tiny particles, then impaction is the main mechanism that works there. And so a typical loading rate would be 120 cubic meters per day for every square meter of surface area. So if we're talking about the sand filter that is shown here, you'd find out the area of the sand just by multiplying the length times the width. You'd find the surface area of the sand, and then the water that's being applied to it, you'd know a volumetric flow rate, cubic meters per day, divided by the area of the sand filter. And so we can actually get a pretty high rate through, up to 235 cubic meters per day per square meter have been used in some locations. But if you're going to use a very high loading rate like that, you have to have very tight control on the quality of the water that's entering the filter. So that means you have to monitor the coagulant concentration almost continuously to make sure that all the particles that come into this filter are in fact neutralized. Because if the particles aren't neutralized, then they won't stick. In the homework that you just turned in, one of the problems says, what if at nighttime you turned off one of the filters? In the homework that you just turned in, there was a process that was happening in parallel. You've probably heard of parallel versus series before. If there's 3 filters in series, then that means the water goes from one to the other. This is a sketch of water flowing in series, and parallel means that the water is split into 3 separate streams. Okay, so this is parallel. In water treatment, we have to build in redundancy, meaning, what if one of the filters needs to be maintained or repaired? So you take one offline, there's still 2 that are functioning. We don't, in our sand filter, have just one gigantic sand filter for the whole water treatment. We break it up into parts because sometimes you're going to be backwashing one of the filters. And we want to produce water continuously, all day long. And the backwash cycle maybe only takes 30 minutes or an hour or so. But even still, when you're going to the trouble of making a water treatment plant, you don't want it to just be temporarily offline. And so if you had 3 of these, then that means this one can be backwashing and cleaning the filter, and these 2 are still operational. So you can go through a cycle of taking one of them offline for repair or maintenance, and then there's backups. That's the issue of redundancy. This diagram is just showing, don't make one huge filter, make a few different smaller filters. So the question is, how many filters do you need? You have to look at how long it takes to backwash to answer that question. And another thing that when you're designing these, the operational consideration is the filter media size. If you're only using sand, then you may not be able to remove as many particles as if you use some sand, some crushed gravel, and some crushed coal, like anthracite coal. And a monomedia filter is one that only has one media. That's what monomedia means. And there are plenty of places where they're only using sand. But the problem with that is that if all of the voids are the same size, then it's common for the filter to get clogged just at the top layer. It doesn't pass a variety of particles through. So filter bed utilization means that the sand filter, if you only have one size of sand, then the particles are coming in, and so the part that's dirty would be this upper layer would be dirty, and then all the rest of it would be clean. And so it's kind of pointless to have such a thick sand filter if it's always the same top layer that gets dirty. So it's an advantage, instead of having only one media, like only having sand, if you had a filter and some of it is coal, and then some of it is sand, and some is gravel, the advantage of that is that it would use more of the depth of the filter. It doesn't clog as easily if you have different types of media. And so a dual media filter or a multimedia filter, the advantage there is you can have a variety of density of the filter media, different particle sizes, and so greater utilization means better efficiency. And the book discusses that. I'd encourage you, as I often do, to make good use of the money you spent on your textbook and crack it open to read and review from time to time. There's lots of really good information in there. What we're going to do for the in-class exercise today, does everybody have a copy of that paper, the in-class exercise? I'm going to step you through the design process and starting to think about what surface area is needed, how many filters should we break that into, and so on. Okay, so read through the problem statement, and we're going to consider we want to have no larger than 7 by 7 for each of the filter boxes. So you're going to have to try and figure out how many filter boxes you're going to need for this maximum size. This is the maximum loading rate. You can go a little bit over the loading rate. You'll get an idea from that through what I'm asking in the questions. But let me pause the recording and I'll let you get started on the in-class exercise. Okay, let's see if we're headed on the right track with this. You're going to have to convert the flow rate into cubic meters per day, or you can convert the loading rate to cubic meters per second per square meter. I think it's easier to go from 0.83 cubic meters per second, multiply it by 86,400 seconds per day. So that'll tell you the flow rate in cubic meters per day, and then divide it by the loading rate. So you need in total 597.6 square meters of surface area. That's looking down at the filter from above. So that's the top view, looking at the filter, how big it needs to be total. The filter should be 7 by 7, and so if you divide that by 49, that means that you need to have 12.2 filters. And you can't build 0.2 filters. And so in part C, what I'm saying is, what if we're trying to just save the client some money. Instead of building more filters, why not look at building less? Because the loading rate is just a guideline anyways. This 120 cubic meters per day per square meter, there's some flexibility with that, depending on how good your treatment process is. So let's say, what happens if we use 12? Is it going to be okay if we use 12? And so then in part C, I say, if you use 12, what is the loading rate? You have to recalculate the loading rate, and it's very close to 120. We started with 120 as our design guideline, and if you only build 12 instead of building 12.2, then your loading rate is 121.9 cubic meters per day per square meter. So that's okay, right? But then in part D, we start to say, well, what happens if one of them comes offline for backwash? And so I want you to continue the calculations on part D with what if there's only 11 filters? Because you built 12, and then one of them is offline, and so now what is the loading rate if you have 11 filters that are functional? Let me step you through the logic of these last couple of questions here. So in part C, basically it was saying, what loading rate do you get if you only have 12 filters instead of 12.2? So we already did that. But now in D it says, what if you only have 11 filters because one of them is offline? So during backwash, your loading rate would be 133 cubic meters per day, meters per day if we cancel out the units. 133, but it says in part E that the limit should be 130 during backwash. It's okay for us to have maybe 121.96, but we're starting to get a little too high now at 133. Since that's over a hard limit, then we should use 13 filters total so that we don't exceed the backwash limit. So that would mean if you have one offline, then that gives you 12 filters. And so rounding down, like we were hoping we could round down to save the client some extra money, but it didn't work out because of this secondary rule of 130 being an upper limit. Yeah, so there's 11.2, but then there's also the one that's offline being backwashed, and then you have to round up from there. So that's what makes it 13. That's right. Yeah, like the holes will get plugged.
Can I say that if we neglect the backwash,
yes,
it will increase the suspended materials?
Mm-hmm. Yeah. So remember the void spaces, the voids would get plugged. It would start to clog the voids. Yeah.
Okay.
Let me bring the answer that I wrote up on the screen. You don't have to be as lengthy as this is necessarily. I'm just saying that if you never backwash, then the particles that you're trying to remove, those colloid particles that were destabilized, they'll start to accumulate in the voids. So all of the voids would get clogged. The voids will get so small because of the accumulation of the debris that the water can't pass through any longer. So it's not like all of a sudden, it just instantly the filter is clogged. It's a very gradual process. And what you would notice if you're the operator of the treatment plant is gradually it takes deeper and deeper water, more pressure, to push the water through the sand filter. The head loss starts to increase. All right, let's take a final look at our announcements for today. The big thing to keep in mind is that we've got an exam when we meet on Tuesday. So we're going to be here in this classroom at our normal class time, and If you have any questions about the homework assignment, if you want to look over the solution for the one that you just turned in, I've got it here, or you can stop by my office and I'll be happy to let you take a look at it. Well, I mean, that's the same as if I had put it onto... No, I'm not going to post it. That would give an unfair advantage to the students next semester, and I don't want to do that. But you're welcome to take a look at it.